I want to talk to you right now about a special type of series called a P-series. This comes up a lot. I'm not sure why it's always called a P-series. I think it's P's for polynomial. But the general form of a P-series looks like this. I have 1 over n to a power. So maybe they call it P for power, but you don't want to use the word power series. That actually means something different. So 1 over n to a power. And that's just the saying that's 1 over 1 to the power, 1 over 2 to the power, 1 over 3 to the power, and so on and so forth. So this is a very particular type of series that comes up a lot. And it's called a P-series. And specifically, if P is equal to 1, then that power kind of disappears, at least it's redundant. And so you have this 1 over n. And that's a special series called the Harmonic Series. And you'll hear this word come up a lot when people talk about sequences and series. They'll say the Harmonic Series. And but the real kicker here is that if P is greater than 1, the series always converges. Doesn't matter. If I look at this thing and it's like 1 over n squared, or 1 over n to the 1.5, or 1 over n to the 1 million, doesn't matter. Guaranteed to be convergent. Super nice, right? Not a problem at all. Now, if it's equal to 1, so in the case of the harmonic series, or if it's less than 1, so like let's say P was 0, or it was negative, or something like that, guaranteed divergence. So it's really nice because just kind of like what we were talking about with the integral test, you get this guaranteed convergence or guaranteed divergence. It's very unambiguous, very nice. So the way we can kind of show this is we can break it up into 4 particular cases. So we can say, all right, let's look at the case where P is actually just 0. So the power, the power there is 0. Well, 1 over n to the 0 is just 1. Well, if I sum up 1 an infinite number of times, I'm going to get infinity, right? 1, 2, 3, 4, 5, it just keeps going. Now, in the case where P is negative, then 1 over n to the P, that's sort of like n to the negative P because P's negative. So I can rewrite that as n to a positive power. I know that's a little odd. But if you think about this, this will be 1 to something positive, 2 to something positive, 3 to something positive. Well, each of those numbers is going to be larger than, or at least as large as 1. So no matter what, if this thing was already infinity and this thing is, and this is even bigger, it's definitely going to infinity. So definite divergence. Now the third case I want to look at is where P is positive, but not the case where P is 1. So hear me out here. What you're going to get is, if you think about 1 over n to the P, where P is a positive number, the graph has the sequence there is these kind of dots. And I can draw a function, 1 over x to the P, that has that. Hopefully you know by now that 1 over x to a power as a function always kind of has that concave up, decreasing function, the very classic, sort of like roller coaster type of function. So they all look like this. So we need to, okay, well that's really interesting because, well look at that, that's a continuous function and it's a decreasing function, which means we can use the integral test to poke at it and evaluate whether it converges or diverges. So if I take the integral here, I get x to the negative p. Well, I can rewrite that, as x to the negative p. And then I add 1 to the power and divide by that new power when I take the antiderivative, and I'm going from 1 to infinity. Now, I don't need to worry about what the 1 is. I don't have to worry about this 1 here. The reason I don't have to worry about that 1 is because this is some finite number, and that'll just be 1 to a power. So it's finite. So if it's finite, it's going to converge. But this infinity may cause it to diverge. So what we need to do is we need to keep analyzing this. We say, okay, well, if P is actually less than 1, then, if I subtract P from both sides, I get that 1 minus P is actually greater than 0. So 1 minus P, this is a positive number. Why does that matter? Because x to a positive number, as x goes to infinity, will go to infinity. So what that tells me is that if that power is less than 1, this integral will diverge because the power on x will be positive. But if p is greater than 1, again, if we subtract p from both sides, we get that 1 minus p is less than 0. So 1 minus p is actually negative. So x to a negative power, or you could think of that as 1 over x to a positive power, as x goes to infinity, actually drives down to 0. It drives down to 0. So what we can see is that if p is greater than 1, you're going to get convergent behavior every time, but you're not in this case. But we didn't consider the case where p equals 1 because this integral doesn't work for that. Right? If we tried to say p equals 1, we'd have a blow up here. It wouldn't make any sense. Remember, we have to use a special case where 1 over x antiderives to natural log of x. But if you do this, natural log of 1 is 0. Natural log of infinity is infinity. So it also diverges. So what this does is just reinforces the fact that only in this case, only in the case where p is greater than 1 are you going to get convergent behavior. But that's super nice, right? Because, now that we've gone down the list, you say, okay, well, what do I need to do? What are my steps? Well, we do that sort of nth term test for divergence. And what you would find actually is for these, the nth term test for divergence would also blow you out because the limit of the sequence is not 0 there. The limit of these sequences is not going to be 0. So since those limits are not 0, the series is going to diverge. But over here, they might. So in this case, you couldn't just use the nth test for divergence. What we've done is actually done the next step, which is the integral test. But what we now have is a shorthand that says, if it looks like this, I don't have to do an integral test. I know that it's going to converge. So this is kind of a shortcut for this particular thing. And we're going to do some examples and put this to use so that we can save ourselves some time.